This is an instructional video on the use of the ARSC wire saw, and I'm going to give you an equipment overview so you understand what all the different parts are and why this machine is designed the way it is. So first of all, our wire saw is housed within a fume hood. This is because even though we do most of our cuts with a lubricant delivered to the cut site to keep the lubricant, removing cut material, and also to make sure that we don't accidentally volatilize any particles that could be harmful if humans breathe them, it's again kept inside of an enclosure. And the light switch is right over here. So once you take a look at the wire saw, I'm going to walk you through some of the different parts and the basic design of construction. So the wire saw holds your sample in what we call a goniometer, and it moves in several different axes. It can rotate, it can tilt, and then this cross vise allows you to move your specimen plate back and forth so that you properly position the spoil board, that is this aluminum oxide or this graphite block, underneath the wire blade, which rotates continuously and saws through your specimen. So that fits something like this. This little hose delivers liquid coolant to the cut site. We have a touchdown stopper, which will basically halt the depth of the cut. And then you have a micrometer stage here, which allows you to index the position of your sample in very, very small increments to make very, very thin slices of your sample. This is the drive wheel, which is connected to the motor, and it is a RPM controlled motor. These two are guide wheels, which keep the wire rotating in a fixed plane. And this is the tensioner wheel. The tensioner wheel is what keeps the appropriate amount of tension on the wire so that it is neither too tight nor too loose. Once you lower the swing arm down onto the surface of your specimen, this top balance weight is what dictates the amount of pressure that's being applied to the cut site. And this back balance adjuster is what allows you to make sure that the arm remains in a neutral position when this slider is not engaged. And it moves back and forth along this rail depending on how much pressure you want to apply to the cut. As I mentioned before, this little nozzle is going to deliver water to the cut site, and you manipulate it to fit directly over your specimen. It is fed from a recirculating pump and reservoir that is kept down here at the bottom of the fume hood, and it's fed up through the deck. A few other things that you'll need to use when you're working with the wire saw is, again, an aluminum plate which chucks into the cross vise. On top of the aluminum plate you have your spoil board, and then you mount your specimen on top of the spoil board. This is basically a landing site where if you cut into it, it doesn't really matter. It's meant to be spoiled or ruined as you stop your cuts. Inside our little tray here, we have a few other things that you'll need when you're manipulating and mounting your specimens. A couple of sets of tweezers, a diamond scribe in case you need to cleave up a crystalline substrate specimen to make it smaller before you mount it. In this case, I've used a piece of silicon, and it cleaves at nice 90-degree angles here. This is what you call a dressing stick. It's made out of silicon carbide, and you use this to remove any resinous or gummy material from the blade if it slows down cutting. These are some practice glass slides and silicon chips you can use for training or just verifying that the tool is working properly. And then you have a block of wax with a small piece taken off here. This is what you use to adhere your samples to the spoil board, and the wax dissolves in acetone. A few other things around the corner. You have a heat gun, which is used to melt the wax, and a stinger vacuum, which can be used to clean up the wet mess that you tend to make whenever you're utilizing this system, and again delivering recirculated water to the cut site. In the event you are not able to effectively cut through your specimen on the wire saw, one of the reasons might be that it is a resinous material or something that is kind of a plasticky style of material. In general, the wire saw is really only effective at cutting through materials that go through conchoidal fracture. That is, they throw off chips or break and fracture, much like crystalline substrates like silicon or gallium arsenide, or things like glass, which again are very brittle. It is not good for cutting rubber or plastic. If you do have those kinds of plasticized specimens, you can attempt to cut them in our little chop saw, but you must use the dry vac to make sure that you're siphoning up the particles so that you don't accidentally breathe them or make a gigantic mess inside of our system. The wire saw is obviously a cutting tool, as is our little mini chop saw. So as with any cutting tool, there is a general sharps hazard, but more to the point, this wire saw has a rotating wheel right here. So there's a mechanical pinch hazard. You would never want to get your fingers bound up inside this area or have any loose articles like my lanyard here or any loose articles of clothing or hair get caught up in this wheel. So make sure that you're being careful. You'll also notice that the swing arm has a pinch point here, and then of course pinch points as you lower it down to these spots. So just be careful when you're transitioning the wire saw to a different point, and definitely don't reach in or get any part of your body, clothing, other things that stick off of your person anywhere near this rotating wheel when it's in motion. By the same token, fingers should never be put anywhere around this area when you're actuating the chop saw. Second thing we need to talk about in terms of safety is a heat hazard. So recall that we're going to be using a heat gun to heat up our spoil board and melt wax so that we can apply our sample to the surface. Keep in mind that the spoil boards may retain a certain amount of heat over time, and so you shouldn't immediately pick them up after you've heated them up to a couple hundred degrees centigrade to melt the wax. Make sure you give them sufficient time to cool so you don't get a contact burn. And then finally, as with any scenario where you're cutting material, when you have an abrasive sort of a situation where you're grinding through or cutting through material, there's a possibility that you can volatilize particles that are not healthy for humans to breathe. So for that reason, on the wire saw, we always maintain a flow of water. In this case, it's the lubricant for the cut. We maintain a flow of water at the cut site so that if any particles do get dislodged from the specimen as your wire saw is eating through it, they get trapped inside that matrix of water and get flushed out down to the drain. So just make sure that you're always keeping the cut site lubricated so you don't accidentally volatilize things that you don't want to breathe. This is especially important if you're working with any kind of 3-5 material, either in thin film or if it's your substrate. So this is things like gallium arsenide, indium antimonide, basically materials that are just not good for humans to get exposed to and absorb into their bodies. And by the same token, it's even more important when you're cutting these kinds of materials on the John Job saw, anything that's resinous or plastic. You don't want to burn through the material, so we use a high-speed chop saw. You execute the cut quickly, but that will also tend to make powder, and you want to make sure that you keep all of that powder trapped within this space. And for that reason, you must remember to work at sash height. So you must keep this guy down so that the flow across the sash is sufficient to keep anything from coming out of the fume hood enclosure at you. And further, we ask that you use the little vacuum here to make sure that you have proper extract so that you're siphoning away any of the material that you evolve from the cut site when you're doing this kind of a dry cut. So just to recap, mechanical / cut hazard, heat hazard from the use of the heat gun, and inhalation hazard from volatilizing particles. And we have several ways to address that within the SOP, so please make sure you follow those rules. When you first approach the space, you should notice that the hood sash is at or below the safety height. It's actually best to make sure it's all the way down. That way, if there does develop a fire in the building, you're not inadvertently pulling more air past the fire. So always leave it down. And in this case, you can notice because the lights are off, the blower on the roof is also turned off. In order to turn on the lights inside the fume hood and also start the blower, you'll come over here and flip this switch. Lights come on, and in just a moment you'll hear the blower kick on. So I'm going to examine and make sure that the previous user left this space and this equipment in a properly idled state. So here we go. The hood sash was down all the way. We verified the power strip is off. This power strip feeds 4 different things: the John Job chop saw, the wire saw, the heat gun, and the recirculating pump. All 3 of these guys, the chop saw, the wire saw, and the heat gun, have secondary switches. Switch, switch, and on the base of the heat gun, the recirculating pump will immediately turn on as soon as you flip this switch. So please make sure that this nozzle is pointed towards the drain hole, just as you see it here. So we now want to make sure that the swing arm is raised all the way, so lift it up in this position. We make sure that the passive wheel set screws are tight. Again, this is drive wheel. These 2 are guide wheels. Your cut happens in this section, and the tensioner wheel is tensioned by this armature and locked into place with 4 screws that are back here behind the swing arm. So there's 4 knurled knobs I'm reaching back here and just tightening righty-tighty or clockwise as you're turning the screw. Next thing you want to do is make sure that the blade is in fact in line with the guide wheels. You'll notice that on the passive wheel and all these other wheels, passive guide wheels and the drive wheel, there are actually two slots where you could have two wires cutting at the same time if you really wanted to. We just keep one, but just make sure that it doesn't jump from one slot to the other slot. Then you'll have a diagonal cut, and that's not going to be good. All right, so after you verify that the blade is in line with the wheels, then you're going to make sure that there's an appropriate amount of tension in the guide wheels. So you basically place your finger somewhere in here where you see the, between the two guide wheels, and just press up. You should see approximately 3 millimeters of deflection. We'll get a little closer. So something about like this. Don't rub your finger back and forth. You don't want to give yourself a cut. Just press straight up. All right, please make sure the top balance weight is slid all the way towards the right, all the way to the back. Then we're going to verify that the micrometer gauge here is dialed all the way to the 0 position, and that this guy is turned off. The coolant pipe, where we deliver the water for the cut site, must be diverted towards this drain hole right here. And again, you want to make sure that this is in place before you ever turn on the power strip here, because it will immediately start flowing water as soon as you turn it on. And then finally, the previous user must have left this area clean and dry. So there should be no orphan specimens, there should be no powder residue all over the place, and the surfaces of the wire saw must be wiped down so that they're not left wet. That can lead to damage in the instrument and rust and all kinds of things. If you find that any of these parts of the pre-flight check are not satisfied, it doesn't mean that the tool is inoperable or that you're not allowed to use it. It just means that you need to make sure you notify ARSC staff so that we can find whoever left it in an undesirable state and remind them of their duties as a good citizen of the ARSC. This is step 2 of the SOP, selecting and preparing a spoil board. Most of the specimens that people are going to cut on this system are generally going to be thin, flat things that they are about to go do electron microscopy on. You need to cut these things down to fairly small sizes so they fit in the chamber, and more to the point, for transmission electron microscopy, you'll be taking a series of additional steps to thin your specimen to electron transparency. So, most people end up taking an aluminum block and mounting their specimen onto a spoil board, which is also affixed to the aluminum block. As you can see here, I have my aluminum block, I have an aluminum oxide spoil board. It's been super glued to the surface of this aluminum, and I have my sample adhered to the surface with mounting wax, and the mounting wax was melted using the heat gun. So you can select either a graphite spoil board or an aluminum oxide spoil board. It's really user's choice. Sometimes it depends on whether or not you're particularly worried about some kind of cross-contamination, but at this stage of your sample preparation, you probably don't need to worry about cross-contamination. There are many, many more steps you're going to go through where you'll have an opportunity to clean any residue that results from this wire saw cutting action. There are certain times when you may have a brittle sample that you need to cut that does not have a simple form factor or doesn't have a flat that you can easily attach to a spoil board, and for that reason we've put together this small jeweler's vise. There are a few other attachments you can mount in here if your sample might accidentally be crushed, but again, this is really made to hold on to specimens that you could not otherwise mount to a flat surface with wax. So this is one other option for you. If you have any questions, please contact ARSC staff and we'll be happy to help you find the right solution for what you want to do. When it's time to mount your specimen onto a spoil board, you're going to collect a small bit of wax. If this has been used up, you can just break off another chunk from our reservoir here. You will take hold of the heat gun from around the corner and prepare to heat up the surface. This is what adjusts the temperature. I usually crank it all the way up, and then there are two different set points for the heat gun: low, or I guess medium, and high, which are indicated by these 2 points here. Having this thing dialed all the way to the right and in the first heat position is generally sufficient to melt this wax, which turns liquidy at about 135 centigrade. I will not have power to my heat gun until I energize the power strip, and remember that I must verify that the hose here is aimed towards my drain port before I turn this switch on. Otherwise it will just start gushing water in whatever haphazard direction it's pointing. So now that I've verified this is pointing towards the drain hole, I'm going to go ahead and energize this guy. You can hear it starting to pump just a little bit, and then there's the water that's coming out. In a later stage, you will adjust the amount of water flow by turning this valve back and forth. But now that I have power to my heat gun, I will simply heat up the surface by aiming the heat gun nozzle directly at the surface for approximately 30 seconds. Again, this guy's cranked all the way to the right, and I'm on the first stage, or this blue with a Roman numeral 1. I aim the nozzle directly at the surface, and I'm taking care not to touch the nozzle. It gets very hot, nor do I want to move my hand into the heat stream. Once I've heated up the surface for approximately 30 seconds, I will turn off the gun, set it over here, and rub a little bit of wax on the top surface. Didn't quite get hot enough. Let's go for high speed. So again, once you get some sort of a liquidy coating on the top surface right here, just enough to hold your sample in place. It only needs to be a few microns in overall thickness. But you've heated up the sample surface. You can see there's a little bit of a liquid, sort of a sheen to the surface now. And then with your tweezers, either your very own that you brought with you, or one of the tweezers that we provide here, you would take your sample, place it on the surface before the wax cools, tamp it down to make sure it's properly secured to the surface, and then let it cool for approximately 120 seconds to make sure it's properly fixed. You'll notice that in this particular mounting paradigm, when we insert the aluminum block into the cross vise, you're going to want to make sure that you've oriented your specimen in a particular orientation to make your cut effective. And the proper orientation is to have the long edge of your specimen perpendicular to the long edge of the aluminum block, like so. This is a bad mount, this is a bad mount, this is a bad mount. You always want to have your sample, again, with its long axis perpendicular to the long axis of the aluminum block and relatively centered within the spoil board. I've let my sample cool for approximately 120 seconds, so now I'm certain that it is adhered to my spoil board. I can always, of course, get a pair of tweezers and just make sure that it doesn't come loose whenever I try to move it back and forth. Now I'm going to put up my heat gun, and we have just this little hook here. It hangs on a command hook around the side of the corner here. Again, just be careful about touching anything around the nozzle here because that still may be hot. So we're going to hang this guy back up, let him dangle there. Okay, so now it's time to mount my specimen block into the wire saw, and we're going to preset the wire saw to make sure that several different things are accounted for when it's time to approach my sample and make a cut. So the first thing I'm going to do is drop my aluminum block into the cross vise, and you can see that these two set screws here are what are going to hold the aluminum block fixed into the cross vise. So once I tighten these two down, it won't move anymore. And that's going to allow me to drop the wire saw onto the surface of my specimen somewhere, but I'll be positioning the cross vise to make sure that that's correct. Next thing I'm going to do, we're going to make sure the tilt stage here is facing towards me so I can see the vernier gauge here, and my rotation stage should read 90. If for some reason you can't see the tilt stage, it's probably because someone has rotated it all the way around, and you'll notice that it's reading the wrong number. So make sure you can see the position of the tilt stage vernier, that's this part of the goniometer, and that the rotation axis is right on the 90-degree mark lined up with your 0 on the bottom. So that can lock in place here with this set screw. I'm now going to, again, make sure that my sample is going to be in sort of the appropriate orientation and position by moving it within this goniometer to align it with the blade. So the next step is to lower the swing arm and move it to a horizontal orientation. And what I'm really looking for here is I want it to remain stable when it's held in this position. So So if it doesn't stay in position when you let go, you're going to adjust this back balance weight in order to keep it in position. And normally it's just a few turns to make that stable. There's a large mass inside here that you're using as a counterbalance around this particular fulcrum. So now that I've got this thing, dialed in properly, you can notice that the swing arm is holding in a horizontal state, sort of hovering above my specimen. All right, now I'm going to make sure that my top balance weight is moved forward to apply a specific amount of pressure to the cut site. And in general, it's best to go with lower pressure rather than higher pressure. So what we've designed here is on this little slider arm, you'll feel as you move this top balance weight, there are little detents or little spots where the weight wants to sort of park itself or snap into a specific position. And there are 20 of those detents as you move along this length. The default position that we've suggested for users to start with is the 5th position, or the 5th detent. So if you hold this little guy, you can feel 1, 2, 3, 4, 5 little spots where it catches as it moves along the rail. And then of course we've marked that here for you with Sharpie, so it's easy to remember that's the 5th position. So now when I hover this thing over in its position, you'll see that this additional top balance weight is enough to drive the arm down from what was a stable horizontal position to a position where it engages with the surface of my spoil board. I want to engage with the surface of the spoil board first because that's what's going to determine the total depth of my cut. If your sample is accidentally in the way, and that would look something like this. So if your cross vise were scooted forward and you accidentally land on your sample, loosen these 2 set screws that allow you to move the cross vise, scoot it out of the way so that the wire only lands on the spoil board and not on your specimen. The reason for that is that you want to make sure that you're adjusting the wire, the tilt stage, so that your spoil board is perfectly parallel to the wire. And in this case, that looks pretty good. I wouldn't want to engage it in any other fashion because it will sort of disturb the mechanism by which I'm cutting the specimen. I need to basically approach the surface with my wire parallel to the spoil board. If that were not the case, then you would loosen the set screw for the tilt stage. That is found in the rear. There's a small little knob back here. Let me move this and show you. This little guy. And you would adjust the tilt of the stage back and forth. You can see right now we're on a tilt of 20, but you can loosen this guy and tilt it back and forth depending upon the shape of your particular specimen. If your sample is flat, I would suggest that you start at a position of 20. And again, that's what allows the wire to stay parallel to the spoil board. The next thing you're going to do is adjust the stopper so that it is going to prevent further descent of the swing arm once you've cut all the way through your specimen. And the simplest way to do that is to look at this guy from the edge, right about here. And what you want to see is about a 1 to 2 millimeter gap between the edge of the swing arm and the surface of this little stopper arm when the wire is touching down and fully engaged with your spoil board. If you need to modify the position, this thing just moves back and forth on a little screw arm. So very straightforward. So now that my wire is perfectly parallel to the surface of the spoil board and fully engaged, I make sure that I have a small gap here between the stopper arm and the swing arm, and that will basically mean that I cannot cut any deeper than this particular elevation or this particular descent of the swing arm. Now that we've preset the wire saw by making sure our wire is parallel to the spoil board, by adjusting the tilt in the goniometer, and we've also set our stopper position to be a millimeter or so below, just enough to where you can see a little air gap between the bottom end of the swing arm and the stopper here. Once I've got that set, I'm going to raise my swing arm up out of the way, and I'm going to loosen these 2 set screws that are closest to the drive wheel and slide my cross vise back and forth until I can descend the wire and make it land not on the spoil board, but now on my actual sample. And you have quite a bit of latitude to move this guy back and forth. what you want to do is make sure you've aligned your wire so that it is going to cut through a portion of your specimen that will be your first cut. And for the most part, this first cut is going to be a throwaway piece. It's something that you're going to get rid of because you need to establish a clean cut surface, you know, a true surface from which to execute your other fine cuts that will have a thickness or a width, if you will, defined by how far you've translated the micrometer. You can't really eyeball a cut by moving the crossvice back and forth to get something 100 or 200 microns wide. It's just not, you're not that sensitive. So the first position you're cutting is just to make a clean surface from which you will then execute further cuts. So in this case, you can see I'm going to cut off about 3 or 4 millimeters length on this side and only about 2 millimeters on this side. So I'm going to square up the end of this little silicon chip. Once I've got that position defined, I'm going to lock the position of my crossvice by tightening these set screws. And I'm going to go back around one more time and just make sure all set screws are tightened. These two hold the aluminum block into the crossvice. These two hold the crossvice into the goniometer. This one is to adjust the rotation of the goniometer. And remember, there's a little hidden one back here which allows you to adjust the tilt of the goniometer. When you engage the wire with the top surface of your specimen, the same general methodology is true. It must be perfectly perpendicular to the top surface of the specimen. It must fully engage with the entire surface or your cut is going to have problems. So, now that we've aligned this guy, we're going to be ready to start our first cut. And we must raise the swing arm before we turn on the saw, but we've got our sample in position. We are now going to prepare to cut off a portion of this specimen, or to wire saw through a portion of this specimen. So we must verify that the water nozzle is pointed towards the drain hole, and it is. Our recirculating pump is already on, and again, I can adjust the amount of flow by toggling this valve here. You generally don't want to close it all the way down. Always leave some amount of trickle coming out because you don't want to deadhead the pump. You don't want to make it try to compress its fluid and push it into something that's a brick wall. That tends to overheat the pump. All right, the swing arm is up and our power strip is on. So now we're going to turn on the wire saw. And remember, in the pre-flight check, we already verified that this was turned fully counterclockwise, but I'm just double checking. I'm going to turn on the wire saw, and it's very important that you establish the speed of the saw, that is the speed of the rotation here, before you engage with the sample. You mustn't change speed when you're engaged with the sample or the wire may bind, which will cause it to snap. So I'm going to slowly increase my RPM, and you'll see that the wire finally starts turning its drive wheel at about 50 to 70 RPM. I'm going to keep increasing to a default set point of 500 RPM. You cannot turn this wheel any faster than 900 RPM, so 500 is a nice middle of the road kind of set point to start at. So I will adjust my speed and get to 500 RPM. And now that the wire is moving, I'm just watching to make sure I don't see any strange wiggles, nothing, no strange vibration, and I'll be ready to engage with the surface of my specimen. So the coolant valve is open, and we're going to direct the flow of the water onto the surface of this specimen. You'll notice that the way this wire saw is shaped, there's sort of a platform here and a bowl in the base here below the goniometer that basically funnels all that water down to a drain port, which flows back into the bucket and then gets recirculated back up to the same nozzle. As you're moving this nozzle around, please take care not to just grab it from the end and start yanking it back and forth. You may accidentally snap off one of these little legs right here, and then water will just be gushing out of the top surface. So it's best to hold the base near the valve and slowly reposition this guy to the point where the water is being delivered to the sample surface. That's an egregious amount of water. I don't really need that much to flush the cut. So I just need some amount of water flowing out that will sort of irrigate and flood the surface. And as I descend the wire saw arm onto the cut surface, I may need to move this out of the way slightly so that I don't run into the wire. And then again, you just want to make sure that you position this nozzle with the wire engaged in the surface so that you're flushing away all of the debris that gets removed from the cut site, in addition to keeping the cut site cold so that you don't overheat the wire. As soon as I have my sample engaged with the surface and I have repositioned the nozzle, I'm going to bring the sash height back down so that if there is any volatilization of particles, they go up the flue instead of coming out here at me, so I don't want to breathe them in. All right, so I'm going to grab the end of the swing arm, drop it down, make sure I just missed my little guy right here, and then I'm going to let it engage with the surface, and then I will reposition my nozzle to make sure I'm flooding the cut site. Now it's simply a matter of watching down here to see when the swing arm descends all the way down and touches down on the swing arm stopper. That means that I've cut all the way through my specimen and partially into my spoil board, at which point it's time for me to stop this first cut, and then I can move on to subsequent cuts of a defined thickness. All right, so my second cut of a defined width of 200 microns is now complete, and I can tell because the swing arm stopper has contacted the swing arm itself. So if I were interested in making additional cuts, I would do so as follows. I can remove the wire from the surface of my specimen, turn off, then I can turn my micrometer back on. It remembers that I was at 620 microns, and if I wanted to make another cut at the exact same width, another 200 micron cut, I would need to translate again this same distance, so that would be 1.24 microns. So here we go. And again, I'm just going slow because I don't want any backlash in my micrometer. There we go. All right, so power back on, drop the wire, engage with sample surface, and verify coolant delivered to the site. In this fashion, you would continue cutting over and over and over again until you had made the desired number of cuts in your specimen. And if you had applied a sufficient amount of wax to the underside of your sample before you mounted it, none of these pieces should be flying off or coming loose from the spoil board. If that does happen in between cuts, it's okay. You just need to reach in with a pair of tweezers after you've disengaged the wire and turned off the motor and remove that piece for subsequent cleaning. When we're all finished with the number of cuts we want to make, we'll need to remove our sample rather delicately because these are tiny, tiny shards of silicon now. And one of the simplest ways to do so is to immerse that top surface in a pool of acetone. So acetone will dissolve the wax, and it will do so slowly over time. And then you can carefully lift out your specimen and finish rinsing it with some other solvents to remove any acetone or wax residue that remain behind, typically methanol and or isopropanol. If you're in a hurry and or you want to unmount a very large portion of your specimen where it would take a long time to undercut the wax using your acetone, you can also remove the aluminum block from the sample surface, put it here from the goniometer, put it on the surface, and reheat your sample using the heat gun, and then carefully use tweezers to remove it with and keep in mind it'll have some hot wax adhered to it. From there, you can dunk it in a small tray of acetone or just use a rinse bottle to wipe off the rest of the wax residue. So after this second cut, we're going to go ahead and remove the specimen, and we'll take a look and see how good we are at resolving a 200 micron wide sliver of silicon with our bare eyeballs. So cutting through this approximately 500 micron thick piece of silicon takes approximately 3 minutes using these conditions. And again, what was the user in charge of? You were in charge of the position of the top balance weight, which was in the 5th detent or 5th position, and you were in charge of RPM, which in this case was set at 500. If you look down here now at the swing arm stopper, I can see that there is a much smaller and nearly imperceptible gap between the bottom of the swing arm and the top of the swing arm stopper. So my cut has basically made it all the way through my silicon piece, and it has now crashed onto the aluminum oxide and started cutting through this. So that's basically defining the depth of my cut, and now I can move on to my subsequent cuts, which will have a known specific width to the cut. This first piece again is kind of a throwaway. Now that I have a trued up edge, I can cut some very specific, very dedicated widths of specimens, again typically for a subsequent preparation for TEM analysis. So I'm going to disengage my swing arm from the surface of the specimen without changing speed. I must retract from the specimen before I can change speed. So I'm going to move the arm up out of the way, being careful not to clip the edge of my water nozzle. And now I can simply shut off the motor. I don't need to worry about changing my speed because I'm going to go right back to 500 RPM. So I'll just re-engage it as soon as I'm ready to make my next cut. Now that I'm not cutting anything anymore, I can go ahead and raise the sash to give myself a little bit better access. And I will move this out of the way for the purposes of filming, but you can see there's a small cut line right about here on my specimen where I cut through that first portion. So now what I'm going to do is use my micrometer to index the whole stage towards me such that my next cut is going to be a defined width. And what's important to remember is that you must account for the width of the desired width of your specimen. In my case, I'm going to go for a 200 micron wide cut. And I must also account for the kerf, or the width of the actual wire itself, which is material that's removed or sort of lost to me. The kerf of this particular blade is 0.42 millimeters, or 420 microns. So that if I want a 200 wide micron piece of my specimen, I must index the stage 620 microns. 200 for my sample width and 420 for the kerf of the wire. So I will turn on my micrometer gauge, the digital gauge, which you don't have to use, but you can. You can change the units here from inches to what's marked ABS, or what all scientists use, that is metric. And I'm now going to index the micrometer to the point where I see it is translated 620 microns. And be careful about going backwards if you overshoot. All micrometer stages have backlash. So this cut should leave me something that's 200 millionths of a meter wide. And the reason that I had to translate further than that, again, is to account for the kerf of the wire. So now that I've got my micrometer translated, I can make my second, third, fourth, fifth, 12th cut, however many specimens you need to make in order to do the next step of your sample preparation. So, going to turn wire saw back on. It will go back up to its target speed of 500 RPM. And then again, I will now descend the wire onto the cut surface and make sure that I'm flooding the cut surface with water. I didn't have to change the position of my swing arm stopper because I'm cutting the exact same specimen. So again, I'm simply monitoring for when does this gap between the swing arm and the swing arm stopper collapse. That is, I can't see daylight through it anymore. That basically ends my cut. Okay, our second cut is completed. You can see that the end of the swing arm has contacted the swing arm stopper. So I'm going to disengage the wire saw from my cut surface. Go ahead and stop it. And at this point, I know that I'm not going to make any more cuts, so I'm going to go ahead and divert my water nozzle back over here, pointed at the drain port. And again, the design of this particular goniometer stage is supposed to let all the water drip off of these ends here and go down into the bowl to find its way back home, following gravity down into the drain port. That doesn't mean that you can just leave it looking like this. We're still going to have to make sure we clean everything up. But let's work on getting our samples removed from our surface here. So, one of the things I think I see is that a thin sliver of my silicon actually came off of the surface. So I'm going to be very careful when I remove my aluminum plate from my cross vise. And down here below, next to the reservoir for your cut fluid, there's a Pyrex dish with a sealable lid labeled acetone. I'm going to set this guy right here, and I'm going to use that as kind of a basin to catch my specimen in case there's anything that may have fallen off of it. So I'm going to remove the specimen plate, set it here, and you can see there are my two little tiny pieces of 200 micron wide silicon. They actually came loose off of my specimen, so they turned loose out of this little cut site right here. But this is manipulating matter down to the several hundredths of a million hundreds of millions of meters. So these things are incredibly fragile, and it may be that you want to try to rinse them off or do something in a little catch basin here where you're not trying to hold onto them or grip them with heavy tweezers. So whether you choose to make a puddle of acetone just on the surface to help release your sample nice and slow, or you choose to use the heat gun, you should feel free to use this dish to make sure that you don't accidentally blow your sample away or accidentally rinse it away where it falls onto a black surface and you'll never find it again. So if you're going to leave your sample in a puddle of acetone, because acetone has a very high vapor pressure, I would strongly encourage you to make a puddle on the top surface and then cover it so that your acetone doesn't all evaporate. If you're going to remove your sample by applying heat, then you would do so in the normal fashion using the heat gun, but I would suggest only going to the low position rather than the high position, because of the volume of air coming out of the end. When you go to high, you may again accidentally blow your specimen somewhere in the fume hood, never to be found again. So you can unmount your specimen using heat or unmount your specimen using acetone, and the subsequent steps for the SOP are going to be basically cleaning up your mess. We are now ready to sort of finalize our cleanup operation. So I have removed my sample from the spoil board using the heat gun. So I heated it up with the heat gun, pulled the sample off with my pair of tweezers, and I'm now going to proceed to start wiping down all the surfaces in here. I've gotten some rags from our rag-in-a-box, which are kept right here. They're usually up here in this corner. And then I'm going to start wiping down anything where I could potentially have slung water. So all up inside the armature, gently down the wire itself. And you can see that I'm picking up lots of this kind of debris. I'm basically trying to make sure that I don't leave any wet surfaces behind. So I'm cleaning inside the armature itself. And it's in your best interest to basically clean from the top down. So if you just remember how water tends to behave, right, it's going to want to drip down in all instances. So if you clean from the top down, you'll have less chance of something you've already wiped dry getting wet because a drip comes down on top of it. I also tend to find larger puddles of water and try to blot those up. So in this sort of tapping action, rather than trying to just smear it all over the place. It's also important to remember to remove your cross vise and wipe this guy down, and that allows you to get a little bit better cleaning done all the way around the full rotation axis of the goniometer and get all those little drips and drabs of water off of that surface. So once you've worked your way past the swing arm and down onto the goniometer plate, make sure that's all clean. Wipe this guy down. Place your cross vise back in, chuck him in place, and the spoil board can simply be wiped off after you let it cool. And be wiped off and placed back in our accessories bin. Okay, so that's clean. I'm now going to make sure that my acetone container is cleaned out. Lid's back on, placed in here for the next user as they see fit. And then finally, I'm going to turn off the power strip so that I no longer have water feed from my nozzle. And this is where I'm going to get down in here below the goniometer and make sure that I don't have any other freestanding water. Or really what I'm doing is trying to shove all the existing water that's in here towards that drain port so that it all gets out of the way. If anything did accidentally spill outside the boundaries of the little catch tray for the wire saw, just make sure that you wipe up any of those surfaces. And again, as a good citizen of the ARSC, we expect you to leave everything as clean or cleaner than you found it. So please help us in doing that part of our mission. So once I've got all my surfaces nice and clean, I'm going to go through the full equipment idle, which returns the tool to the default state we found it in when we first started this whole process. Remember, these are not solvent soaked wipes, so they don't go in the metal trash can, they just go in the regular trash. All right, so moving on to final step, equipment idle. We're going to verify the power strip, the wire saw, the coolant recirculating pump, and the heat gun are all off. So I've toggled all the switches and made sure that the power strip is in the off state. I'm going to remember to rotate the speed control knob all the way to the left or counterclockwise to reduce the speed back to 0. That way someone doesn't get a surprise when they turn it on or energize it. We're going to slide the top balance weight all the way to the right. We're going to verify the wire swing arm is raised. That is correct. We adjust the micrometer to read 0. I'm going to turn on my gauge here to help me with that process. You've rotated back to 0 using the hand portion or the analog portion of the vernier gauge. Reposition the coolant pipe into the drain hole. So again, I'm holding it on the base right here and driving it right back towards the drain hole. So in case somebody does inadvertently turn it on, at least the water goes down the hole. We've already cleaned the equipment in the area, sort of wiped it down. Everything's nice and dry. I'm going to remember to log myself off of FOM and then fill out my end time in the log notebook. Finally, don't forget to close the sash and turn off the light/blower. And now you know how to use the ARSC wire saw.